So my plan is to speak about Chern-Weil theory next time. So today we will have short recollection of what we know. I was trying to write it down on the paper and found it's too much, so we need to make a short recollection. So what we speak about? Locally trivial vector bundle. What is our notation for that stuff? So this is a total space, this is projection, this is a base. Everything is smooth, everything is manifolds. Fiber is field K, which is either real numbers or complex numbers. At some moment, we will speak about complex vector bundles and holomorphic stuff around that. So we will make some, we add some details here. But now we speak about real manifold here, real manifold here. Each fiber is either real vector space or the complex space. Not difficult. Well, very good. So trivializing charts. Yes, trivializing charts. What is that? It's cover and trivializations. U alpha is the cover of the base manifold B, and over each open set U alpha, our vector bundle is trivialized. It means that psi alpha is a fiber-wise diffeomorphism. And what is important here, that psi alpha preserves structure of the vector space over the fibers. It's not just diffeomorphism, but it preserves structure of vector space here and here over each point. To choose such a trivialization, it is the same as to choose frame, local frame. So this thing is equivalent to choose of local frame. This is a collection of sections. E1 of x, blah, 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 ER of x. X belongs to open set U alpha, and these vectors, E1 of x, ER of x, is a basis in EX. So this one is the fiber of our vector bundle over point x. So what is the formula which relates this thing and that thing is very simple. Psi alpha to the power inverse of a point x and a collection of numbers. So this is a vector from KR. So I should write a point in the vectors in the total space of the vector bundle. So I choose the point. So this EA of x is a vector, and I take a sum from 1 to r with coefficients which are written here. This expression has sense because it is expression in the one chosen fiber over point x. So it's possible to write such an expression. It's not possible to write such an expression if I will try to add two vectors, one in the fiber over x and another one over point y. But this happens where? This is here, so it takes sense. This is correct. Okay, gluing cocycle. If you write over non-empty intersection u alpha beta, which is u alpha intersection with u beta. So over each overlap, we can consider function psi beta, psi alpha inverse. So imagine you have two trivializations. One which is written here, and another one, psi beta, which is not written here. So you take representation of a point here as a point in the base and the vector in kr. You go back to the vector bundle and then try to trivialize it in another way. So you will obtain a function of a very specific kind. We wrote it in this way. But maybe V belongs to kr. This object also belongs to kr. And G beta alpha belongs to invertible matrices of size r by r, square matrices of size r by r, and they smoothly depend on the point x from the intersection. So x belongs to u alpha beta. The guy who asked me to write explicitly to which sets belong every letter is absent, but nevertheless I will write it. Okay, what are the properties of the gluing cocycle? G alpha alpha is identity. So how can I write identity? Okay, it's identically equal to unit matrix. Oh, it's not possible to write E because E is a total space. So this is okay. So if the indices are the same, okay, u alpha intersects with u alpha, so I need to write this matrix. This is identity. If you consider g beta alpha and g alpha beta, then at each point they are inverse one to another. And finally we have gamma beta g beta alpha, and this one is equal to g gamma alpha on u alpha beta gamma, provided it's not empty. So on intersection, non-empty intersection of three open sets, three trivializing charts, we see this condition. So if you have vector bundle, if it's trivialized, then you construct functions g beta alpha. They do satisfy these properties. You can go from the other side. You can choose functions which satisfy such properties and restore some vector bundle. Okay. One can say that collection of gluing cocycles is a little bit bigger than the collection of vector bundles, because one vector bundle can be trivialized in many ways, so you can obtain many gluing cocycles. And if you take, it could happen, if you take different gluing cocycles and you construct a vector bundle, then you, from different cocycles, you will obtain the same vector bundle, isomorphic vector bundles. It means that you need to impose a kind of equivalence relation on gluing cocycles if you want to have some kind of one-to-one correspondence between these guys and that guys. We will not need it, so let us skip it. But one can write explicit formulas which says which gluing cocycles are equivalent. Okay, so next thing we need to discuss what are collection of operations to produce new vector bundles. Collection of operations to produce.
So we will not speak about equivalence.
We will skip it until we need it. Maybe we will need it, not need it at all. So let us remind what is a collection of operations which can produce new vector bundles from old ones. What is the name of this operation? Yes, Whitney sum. Tensor product. Dual. Yes, we have a huge discussion. What is the Gluinka cycle for this guy? So we don't need here one because there's only one vector bundle in this construction. Also, we can construct exterior power, symmetric power, and also we have yet one operation. Could you tell me which one? Determinant. Oh, determinant is a particular case of this one, but okay. Good. Home. Okay, this is a great idea to have an internal home in category of vector bundles. So if we have two vector bundles, we can construct new vector bundle, which is E1 star tensor with E2. And in a moment we will discuss how it is related to morphisms of vector bundles. Well, and there was one more, pull back. So basically people draw diagram of such type. So if you have vector bundle E over B and you have a map from B1 to B, then you can construct new vector bundle which is denoted by F star of E, which fits into this commutative square. I hope we remember the definition, so we don't need to write any details. Okay, so morphism. So if I already spoke about category of vector bundles, so we need to speak about morphisms. If you have two different objects, you don't care about, so this is a projection 2, this one is projection y, this one should be commutative, so this is f, tilde, this is f. The map f should be fiber-wise linear. So it preserves fibers because this, so fiber here goes to fiber here, but we require that f is a linear operator. For every point x, which belongs to B1, f from fiber of E1 over point x to the fiber of E2 over point f of x should be linear. Roughly speaking, then we pass to local trivialization, then the map f will become something like field of linear operators. At each point you will see linear operator on these objects. But then we speak about one vector bundle over the same base. Maybe we speak about two vector bundles. If the base is the same, we usually ask the base manifolds to be mapped one to another by identity. Same thing, yes? And if f is diffeomorphism and it preserves linear structures, blah, 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 then f is automorphism of this object. So we can look for something like that. So f is diffeomorphism of E itself, which preserves fibers, which preserves linear structure, blah, blah, blah. In this case, we say that f is automorphism of this vector bundle, and it has very Its name sounds very nice. It's gauge transformation, gauge automorphism of this object. Gauge group. Okay. Let us remind very important why I asked you what is the relation of this thing to this thing. We discussed it on seminars. What is the relation of this vector bundle to the morphism of vector bundles?
The sections. The
Sections of this thing are morphisms of such a structure. And we can say that map F from sections, so if it's k-linear, from sections of E1 to sections of E2. So there is a third object, yes? This third object. We have vector bundle, we have collection of morphisms of vector bundles, and also we have k-linear maps from sections of one vector bundle to sections of another vector bundle. So this one is infinite dimensional vector space, and this is also infinite dimensional vector space. So a condition of this, for this F to be not very good to write F hat. So it's not very good to say that this thing is k-linear because it's too weak condition. You say infinite dimensional, you say, okay, let's consider k-linear maps. This condition is very weak because then you look for map induced by F. In this situation, this will be not k-linear, but also C infinity linear. So I hope we proved that collection of morphisms from one vector bundle to another, or the same base with identity on the base, is the same as C infinity B linear maps from these sections to that sections. And such morphisms are in one-to-one correspondence with sections of this vector bundle. Very good. So now we pass to connections, two connections. We pass to connections. So connection. So it's k-linear map from sections of E to sections of another vector bundle, T star B tensor with E. And the notation for this object is nabla. Okay? The property. This is not linear over functions on the base. It should satisfy something like Leibniz identity. So if there were no first summand, then it would be C infinity linear stuff. So this would be induced by map from this vector bundle to that vector bundle, and then it would give us nothing interesting. But it contains this term. Well, so what we need to understand? Difference between two connections on E is C infinity B linear. Yes, so nabla 1 minus nabla 2 is a section of what? E star, tensor E. Okay, we should write something like to preserve order. Yes, to preserve order. So if you take difference between two connections, then you obtain section of this vector bundle, and then it should look like this. And people say that this difference is one form on B, because we have cotangent vector bundle, cotangent vector space here with values in endomorphisms of E, because E star tensor with E is endomorphisms. Okay, so in local chart, we see that if we have a section as a column of coordinates which depend on point in the base, and we want to write something like apply connection here, then it looks as follows. First summand is just differentials of this thing, and the second is some matrix which depends on X applied to S1 SR. Here I want to indicate that everything depends on the point on X. So differential is taken with respect to coordinates in the base, and now I would ask you to say me what is A. Matrix of one forms, yes. So if I write if I speak about local chart, so I need to specialize open set, trivialization, then I can write this thing. What happened on the intersection? For U alpha psi alpha, we obtain matrix A alpha. For U beta psi beta, we obtain matrix A beta. What is the relation of one thing to another? So we obtained a formula for A beta in terms of A alpha and gluing a cycle. I will try to write this formula, but maybe with mistake. I ask you to correct me. G beta alpha A alpha G beta alpha minus 1 minus dg beta alpha times g beta alpha inverse. Please check it with your nose. That's correct. Very good. Okay, let's go on. So imagine how many things we studied for these 3 lectures. Usually, I need to erase. I never need to erase to make a repetition of key points, but now I need to erase.
May I ask a stupid question?
Okay.
About why it is called one forms with values at endomorphisms? Because for every point in the base,
we obtain a matrix of one forms.
No, I say about difference between connections.
Okay.
Why it is called one forms with values?
Let me explain you. Look here. So this one is one form.
Yes.
E star tensor with E is endomorphism of fiber.
Yes.
That's why we say that endomorphisms. map from here to there.
It is not one form which for every vector gives us an endomorphism.
Exactly. That's correct.
Okay.
Look here. This is one. If you look to local charts, this is an example of connection. So if I take arbitrary connection and subtract this one, then I should obtain linear operator. But this linear operator should be able to take a vector as a source. So this thing is not just matrix. It's matrix which depends on dx1, dx2, blah, blah, blah. So this is a matrix of one forms. This is exactly endomorphism of E, but with values in one form with values there, because you can substitute here vector psi. Then we define a covariant derivative in direction of vector psi. Then we calculate psi here, and also we substitute psi to one of the arguments here. I want to add more details, writing specific formulas. Namely, then you take covariant derivative of a. So let me repeat. So if you look for, if you took local chart, yes, so then you already took a trivialization. That means that you have frame. You have a frame. What is a frame? Let me. I will try to write a formula for frame. What is it? EA of X. So this is a section over of E over U. But how it can be written in explicit terms? Very simple. EA of X is psi inverse of what? So you take a point X because everything happens fiber-wise, so points should be preserved. But here you should write very concrete vector which belongs to KR. This vector consists from zeros and has 1 on the place number A. One of the standard basis vectors. Standard basis vector with number A. So this is a frame because A goes from 1 to R. So this is a collection of local sections. At each point you obtain a basis. So we say about frame. What I want to do, let me ask you, what happens if I take a covariant derivative of this local section? What happens? I will obtain a linear combination of sections, but with coefficients here. This should look like okay? This should look like this one. But A is one form. A and B is one form. Now it's just a usual one form because this letter has indices. So this is a matrix entry of this object. So this thing consists of these functions. So we can write this guy as BAI dxi. In physics, people solved this problem in a very simple way. Namely, you have coordinates which correspond to the ground manifold, and you have indices which correspond to Minkowski space, Greek letters, and indices which correspond to the fiber, so some other letters, maybe Latin, but we use here letters from the beginning of the alphabet and from the middle of the alphabet. But I would prefer to write something like that. But sorry, we will use this notation. And A is a matrix valued okay? Well, and that's why then we write a formula in this way. We need to pay attention to the order of these letters. Never interchange them. This is a joint representation. Never interchange. And also be careful here. Okay? Okay, very good. So let's go on. So next question which we should address should be very simple. Is it true that connection always exists? We have a vector bundle. Is it true that there is a connection there? Yes. How many? A bunch of them, because difference belongs to the section of this thing, and there is a very huge amount of such sections. But before we write it, we need to find at least one connection. Okay, I will show you how to produce it. There are two ways to produce it. One is to embed the vector bundle into a trivial vector bundle of huge dimension and then use projections. But actually, to produce an embedding, I need to use partition of unity. No way. To embed something difficult into something simple, you need to use partition of unity. So, a question. Do a connection does a connection on E exist? Yes. So the construction is as follows. Choose local trivialization U alpha, psi alpha. It should be good enough to existence of a partition of unity subordinate to cover U alpha of base manifold B. So these are two different things. You have trivializations and you have partition of unity. So to have the partition of unity, you need this cover to be suitable for that. Locally finite, blah, blah, blah. So, but it's possible to do that. Notation, rho alpha. Would you remind me, what is the partition of unity? Very difficult question, because it's one of the basic definitions from differential geometry, so everybody forgot it. But let us remind, what is the definition of partition of unity?
It's a collection of smooth functions.
Obviously, this is, okay. Smooth function on the base manifold.
A way for me to remind it is some sort of material chart. There's always something inside something, so I try to always inject those you try to define the small one and then optimize it on the
Mhm.
big one.
Not at all. Okay, so what you said about support?
Support with in the chart.
So this is a number. These are points, yes, such that rho alpha of x is not 0. So we take a closure, and it sits inside u alpha. The role of this function is not matryoshka function. The role of this function is quite simple. You have something which is global, and you want to deal with this object in local chart. But you want this thing to be 0 near the boundary of the chart. Otherwise, you can just restrict, and that's all. But you want this thing to be 0 near the boundary of chart, whatever it means, because chart has no boundary and so on. So if you go inside chart and suddenly you go out of the chart, that at this moment everything should be 0. So this gives you such a possibility. You take function, you take a section, you take everything you want, multiply by rho alpha, and this product will live inside chart. This is a way to localize details into interior of the chart. Other things.
Must be positive.
Okay, rho alpha is between 1 and 0.
Yes, and each point must be covered only by a finite amount of charts.
Yes, so for each point in the base, there exists a neighborhood u alpha. Yes? Such that neighborhood which contains x, such that u intersection with support of rho alpha, maybe with closure, is not 0 for finitely many alpha. Why I wrote here a closure? Maybe it's not necessary. No, I want a closure.
Where you take
In B.
in what?
In B. In the base manifold. People sometimes write it in more rigid way, so they write this.
But when you define support, you take closure
In B, yes.
closed by definition. So why?
No.
Why-
Support
why-
is open. Support is open. Because this is an open condition. You take a preimage of everything except 0. It's open set.
Yes.
And then you take a closure.
Я спрашиваю, почему второй раз замыкание пишут?
Где?
Ну, пересечь с замыканием саппорта.
А, в этом... Ой, sorry, yes.
Нет, там понятно.
Да, yes. Thank you very much.
Да.
Sometimes people write this, sometimes people write that. It depends on your dedication to foundations of theory of differential manifolds. But it means that at each point you have only finite number of these things and final.
Sums to
Yes, sums to 1. At each point, this sum is finite. And moreover, if you take a point in some neighborhood, this sum is also finite. That's why we need this third condition. So for each point, you have small neighborhood in which you have only finite number of functions which are non-zero. So this thing gives you a possibility to localize data, and this thing gives you a possibility to globalize data. In which way? So assume you have something which is defined in each chart u alpha. 1, u alpha here, u alpha here. So you have collection of objects which sits in each own open set u alpha. And you ask yourself, do they define a global object? You say, okay, if they coincide on the overlap, then that's okay. So if you have a function f alpha, which is smooth function on u alpha, the question, is it true that there exists a function f such that f restricted to u alpha is equal to f? Is it true or not?
In general,
In general, not, because there are no conditions. To have this property, you need to know that f alpha restricted to u alpha beta is the same f beta restricted to u alpha beta. So the functions should coincide on the overlaps. On intersections, yes. But assume it's not. So assume you have a collection of functions which sits, each function sits inside its own u alpha. Is it possible to define global object? Something global. It's possible. You write the following thing: rho alpha, f alpha. Now you see that this object, rho alpha, f alpha, can be considered as global. Because look, f alpha is defined inside u. Then you multiply by rho alpha, then you go to the boundary of u alpha, this object became 0. And then you prolong it, define it outside of u alpha as zeros. So this is a global object. And then you take a sum. The sum is not serious because at each point it's finite sum. The question, how this thing is related to this thing? Who knows? Nobody knows. Because if you try to restrict this thing to the chart u alpha, you will not obtain u alpha. You obtain f alpha and some contribution from other things, f beta, which have non-zero intersection with u alpha. But we don't worry about that. The question is how to glue local data into global data for any price. In some situation we need it, like in this one. In this situation we can define connection in local charts, but we want to glue them together into global object. So I will show you how to do it. Let us take connection on E alpha E restricted to U alpha. We denote it by U alpha with tilde. For what reason I write tilde, I do not know. Just to stress that is a local object and not written. So this is not expression for some global connection in chart U alpha. This thing is defined only on U alpha. How to define it? Very simple. You have trivialization psi alpha. No, not B, U alpha. Cross KR. So how to define? So do you agree that we have connection here? Which one?
Differentiation.
Just take an exterior derivative, and maybe you can add some matrix there. So we have connections. We have connections here. Simplest one is to send section to its exterior derivative. Or you, if you want, you can add something, because you don't need to glue them. It's just defining. So then you define connection here. So we have connection. So write it double tilde. So we have connection here, and we want to define connection here. What we do? Nabla alpha tilde is given by the following formula. You send the section of this vector bundle here, take its derivative, take its apply connection, and then go back. So I defined connection here, but this connection is defined correctly only on the trivializing chart U alpha. So now I want to glue them into global object. Okay, let's go. So I need to write a formula. So I want to write a formula for the section. So S is a section of gamma, a section of the initial vector bundle E, is global section. So I want to define. So now I want, what I want to do, I want to make it local. So obviously I want to apply local sections, yes? Because I know local connections, so I want this thing to become local. What I do, I multiply this section by rho alpha. What I obtain? Would you tell me, please? What is it? We can consider this as a section over U alpha, because outside it's trivial. Nothing happens outside. Now I can apply connection here. I want so.
We can simply
Restrict?
restrict, yes.
Okay, you will check if it's possible. So Zhenya suggests the following formula. Rho alpha tilde for S just restricted to U alpha. Me. I multiplied by rho alpha. Zhenya says, you don't need it. Just restrict. Maybe it's correct. We will check. So we have, at this moment, we have local data because this thing or this thing, they do not coincide on overlaps. Obviously. Yes, they do not coincide. And we glue them together by the idea which I showed you. We multiply this thing by rho beta and take a sum over alpha and beta. And Zhenya says that I don't need to do that, just multiply this thing by what? Oh, well, I checked it here. So let us start from my formula. I believe that's okay. First question, is it true that this thing is k-linear? If I multiply this section by a number, it goes out, So it's k-linear, no problem. I need to check the formula, what happens if I multiply f, the section by function f. So f is a function on the base. What happens? What happens? Hmm?
So f goes out.
No. Be careful, because what I write here, alpha beta, yes, rho beta, nabla tilde alpha, and here I write the argument, which is complicated, f rho alpha s. And since this is a connection, then f does not go outside in a simple way. It gives you additional term. What is the additional term? First one is derivative of f times the product of rho alpha and s. And then f goes out. Okay? Let us rearrange what is written here. So first df tensor product with alpha beta, rho alpha s. I believe that this one is just s. And what happens here? Plus f times sum over beta and alpha of rho beta, nabla alpha, rho alpha of s. And I believe that this thing is just nabla of s. Okay? So I proved Leibniz identity. So this is a connection. It exists. Now we check formula which was suggested by Zhenya. So multiply this by function f.
Not in this way.
It was
It's definition, yes?
Beta is outside.
Ah, okay. Rho beta is outside. Okay. So we calculate this thing, yes? We multiply s section by function f. We write rho beta tilde beta f s restricted to u beta. Well, what we will see. df, differential of f, tensor product with nabla beta s restricted to u beta. Maybe it's okay. So I will write it next line. Oh, well, sorry, it's not correct. Yes? So then you apply covariant derivative to this product. You write two summands. First one is df tensor with s restricted to u beta plus f goes outside as he wants, and then you write a covariant derivative of section here, restricted to u beta. So what makes me feel uncomfortable, I will tell you. What you're doing here, you take restriction of s to u beta, then you multiply by this thing, and then you take a sum. Is it true that it will be s again? Okay, so everything is okay except one question. Is it true that rho beta times s restricted to u beta is the same as this?
Yes.
Yes.
By construction of partition P.
Which point? Which are fixed?
In fact, fact, we don't even need to restrict S in the first place, because the sum of rho beta and nabla beta is already defined everywhere.
Sorry?
The sum of rho beta and nabla beta from the very beginning is already
Here?
defined globally.
No, we want, no, wait a moment. Then you want to define this thing, this. You need to consider a restriction of sections to U beta. So this is a local object.
Yes, nabla beta is local, but the sum of these things multiplied by.
This is a global object.
Yes.
Okay. So we have two proofs. It's very good.
May I ask the question about the formula where we define the connection in a chart?
Mm-hmm.
So we take a section and send it to like U alpha times Char that gives us a section of this bundle, and then we take a connection. So that gives us a section of a different bundle, and then we apply.
Brilliant. Brilliant. That's correct. I waited until somebody notes it. Look here. Then you. So let me repeat what he said. So we have section here. We apply trivialization. We obtain section of this object. Then we applied this thing. We obtain section of not of this thing, but this one tensored with cotangent space to trivializing open set. Yes? So this one is not trivialization of this vector bundle, but it's trivialization of this vector bundle. But you see that actually this trivialization psi alpha defines trivialization of this thing, so I add here one more tilde. Tilde is universal sign. Okay? Trivialization of what? E cotangent to B tensor with E. Great. So we have too much information. So now we want to discuss the following thing. Assume as we already discussed the situation, then we have some vector bundles, how produce new vector bundles. We know some tricks. Now imagine all our bundles were equipped with some connections. And I want to produce connections on new vector bundles. So imagine we have E nabla. We have E1 nabla 1. We have nabla 2 on E2 over the same base manifold B. So let us start with simple question. Connection on, and now we give a list. So if I take Whitney's sum of two vector bundles, what do you think I use as a connection of this Whitney sum?
Component-wise.
Yes, because section of this object is two sections, here and here. So nabla of S1 plus S2 is just nabla S1 plus nabla S2. If you speak about this thing on the matrix level, so you have connection form, so it looks like A1, A2. This should be matrix. The connection is represented by a matrix of one form, so it looks like this one. So next question, if we deal with this object, what is the connection here? Leibniz. my background from homological algebra makes me suffer, because every time I write such a formulas, I think about which sign should I write here. Okay, next question, much more interesting. If we consider dual vector bundle, what is the connection there? Actually, the situation is as follows. The definition is not direct. There is no formula. You will produce it as an exercise. Indirect definition, indirect. So sections here of this vector bundle and sections of this vector bundle say S and sigma. So S is a section of E, and sigma is a section of dual vector bundle. So if you have a section of dual vector bundle and you have a section of original vector bundle, you can consider pairing, fiber-wise pairing. And my question is, what's the nature of this object? What is it? It is a function, it is a one form, it's linear operator. What is it? Function, because at each point of the base manifold, it's just a number which gives you a value of sigma on S. So this one is a function. Then I can take the derivative along vector field on the base. So it should be a function again, but the indirect definition says that this function or derivative of this function is just this expression. So then you take derivative of S along vector field psi, you obtain a section. Then you can calculate value of what? Value of section of dual vector bundle. And here you have a value of derivative of section of dual vector bundle on the section of the initial vector bundle. And they are related by this formula. So this is the indirect definition for this thing. So this is a operation which satisfies this property. Exercise number 1. Check that nabla is a connection on dual vector bundle. Find its connection one form. I would denote it by A with check. To be more precise, in terms of A on E. Because you have a connection on initial vector bundle E, so you have matrix valued one form there, so you can solve this exercise. Well, if we speak about this thing, what is the formula for connection here? Like Leibniz, because the section here is just wedge product of some sections, so you can do things like it was done here. Similar for symmetric power. Nothing interesting. So the interesting point is only here. Well, very good, very good. There is only one thing which is left, We will speak about it, then we will be speaking details about complex vector bundles, because if you have a complex vector bundle, you can define so it has complex structure, fiber-wise complex structure, so then you can define E bar. Not dual, but complex conjugate. And one can define the connection here, but actually then you speak about complex vector bundles, you want to add some properties on the connection, and we will discuss it in details later. And before we pass to Chern-Weil theory, let us speak about principle bundle. What does it? It looks more or less the same as vector bundle, but more or less, because principal vector bundle has different fiber, but it has gluing cycles, the same as for vector bundles. So what we have here, we have a total space, and we have a base manifold, and we have projection. So again, it is surjective submersion. And also we have some additional structure here. We have right action of a Lie group G on the total space. And this right action should satisfy some specific properties. What are the properties? Fiber-wise, so if P belongs to fiber over point X, then P, so pay attention please that the action is on the right. So I write the group element from the right to the point pi. So this guy belongs to the same fiber. Oh, why? Sorry. It's not E, because total space is P capital. Well, so guys, very important question. Are you able to track the difference between small letter pi and capital pi? Or should I choose another letter? Справитесь? Нет? Okay. No, so, okay, I write it in a different way, but you can write in the same way. It will be not very good. Let me write here letter Q. Okay? So if a point Q belongs to some fiber, then after action of element G, you still sit in the same fiber. The requirement is that the action is free. And transitive. This statement means exactly the following thing. If you
Transitive on each fiber.
Fiber-wise transitive, yes, fiber-wise. It means the following thing, that if you take point Q here, then you have one-to-one correspondence between elements of the group G and the points in the fiber by the following identification. If you take 2 points in the fiber, then you can move 1 point to another by some element of the group G, and you can do it only one way. It means, roughly speaking, it means that each fiber is the group G itself, but you delete unit there. You don't see identity element. For example, imagine you have something like that. This is tube. This is a fibration with where each fiber is circle, S1. Obviously, you can define the action of the group S1 here. Just rotate each fiber by some angle. But if you look at S1, it has identity, yes? But fiber is diffeomorphic to S1, but no chosen E. No distinguished element here. Okay? A question?
Can you repeat S as S1?
The group S1 has distinguished element, unit. But fiber, which is diffeomorphic to S1, has no distinguished element. This is not all the conditions, because we want this thing to be locally trivial. It should have local trivializations. So it's part of structure. So we still have U alpha psi alpha, and if you restrict P to U alpha, the trivialization gives you product. This one is projection 1. So this diagram means that trivialization is fiber-wise. It preserves fibers. But there is one additional condition. Then we spoke about vector bundles. We claim, we require that psi alpha was preserving fibers and is preserving structure on fibers. So then we spoke about vector bundles. Psi alpha was fiber-wise isomorphism of vector spaces from here to there. What is replacement in this case? Psi alpha should be equivariant, yes. So if you have a point here shifted by group element G, then it should be the same as psi alpha of Q times G. Well, how you understand it? To speak about this, I need to say what is a group action here. Okay, but it's more or less obvious, because I want the action to be from the right, it should be free, it should be blah, 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 so it should, the only way to write it is as follows. So the right action here is from the structure, but right action here is my duty to tell you this is the right action here.
Прям так смело написали свой G.
Что еще раз?
Там написано у альфа на G, правильно?
It's already trivialized. So this is a trivialization, yes. Well, the question which Zhenya asked gives you a very simple statement. Does principal bundle admit a section? This is a question. Then we spoke for vector bundles. This question was absolutely stupid, because vector bundle always admits a section. For example, 0 section. Otherwise, you can take some bump function and 0, 0, 0, something 0, 0, 0. There are many sections for vector bundles. We know that it's infinite dimensional vector bundle, but if we speak about principal bundle, does it admit section or not? Very interesting question. The answer is very surprising. If and only if this this principal bundle is trivial.
By section you mean global?
Yes, yes, yes. Does it? Okay, let me add here global section.
So it is enough to have one global section, so our bundle would be trivial.
Yes. I will write you a formula. Quite simple. So imagine you have I will write you a diffeomorphism of this guy with this one, which is G equivariant. The formula is very, very simple. So you take a point here, X and G, and I need to send it to the point in the total space of principal bundle. What I do, I calculate section at the point X. I obtain a point here. And then multiply it by G. So this thing belongs to P of X. That's all. How to understand that this tube is just product of the base manifold with a circle? How you do it? You just take a continuous family of points on each fiber. Yes, and then you just make a little twist to make this line to be straight as base. Okay? This is exactly what is written here. So the notion of section for principal bundle is a little bit different than a section of. But nevertheless, after you choose trivialization in this way, it means that the restriction of P to U alpha has section of such type. And then my question for you is as follows. Imagine you have two trivializations, psi alpha and psi beta, and I want to write the formula for this transition. So it has X and it has H. X belongs to U alpha, intersection with U beta, which is non-zero. Okay, and G, H belongs to the group G. My question is, what is the formula? How it looks like? Obviously, it should contain X in the first place, because everything happens fiber-wise. Fiber is preserved. What happens on the second place? There should be a group element, yes? And the map should be G equivariant from the right hand. Okay?
XH?
What is XH? Very simple. Let's think about, if you know this thing, you will know this thing. Because since this guy is equivalent, you need to calculate a transition function only on this thing. Yes? Who knows which group element you will obtain in the second place? Nobody knows. So let me write it here. Psi beta, psi alpha minus 1, apply it to this guy, and then multiply by H. Is it correct? Yes? It's absolutely correct. It's H, it's equivalent, so the group element goes outside. We don't worry about that. So only thing I need to understand, what happens to this point. I cannot understand it. It's maybe arbitrary. Yes, okay, we will finish in a moment. psi b, so this is the point x, and something which depends on the point x. Since it also depends on the intersection, so I write it g beta alpha of x. And then h outside, and then finally I put x inside. My question for you, are you familiar with this thing? Why I wrote the same letter as previous letters? Because it's the same. It is the same object, because g beta alpha, this is a function. G beta alpha is a function from intersection to the group G itself. We already saw this stuff then we spoke about vector bundles, but the value of the gluing cycle were in the general linear group. But I already told you that at that moment, so sometimes we could restrict the group to a smaller one. I will explain you this the next time. So I will not ask you to check that this is a gluing cycle, just believe me, because everything is defined by these transitions. So automatically you will obtain the condition on the G beta alphas. So if you have gluing cycle, then you can construct principal bundle in the same way as we did for vector bundles. And I ask you to do it. Exercise number 2. Explain me how to construct principal bundle from gluing cycle. It's not very difficult. You do more or less the same procedure, but just check the details. Okay, we have only 2 problems as a homework. May I ask you to try to do one thing as an exercise? I do not know if you will be able to do it, but let's try. Let's try to do it. Please. So we have tautological line bundle over projective space, yes? It sits inside trivial vector space of what dimension? Maybe, okay, no, don't. Okay, let over projective line, just to have small number of coordinates. So we look for projective line. We have tautological line bundle of a projective line. So a tautological line bundle sits inside trivial vector bundle of rank 2. Yes? Remember it? So my question is how, so since this guy is trivial, you have trivial connection here. If you want to obtain connection here, you do the following. You take a section here, embed it here, take derivative, then project here. Something. So if you want to define connection here, you do so, then projection. Understand what I suggest to do? So you take a section here, you embed it here, you take a derivative. It no longer belongs to this fiber, but you take a projection. My suggestion is to find the expression in local chart. Maybe you need to perform some search through the literature, blah, 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 but it's not very difficult because there are not too many coordinates here. It's a very simple question. So I want to see connection form here and transition matrix. Okay? 3 problems for Friday. And something which is left from previous Friday. So I estimate we have something like 5 problems. 4 or 5. Okay, that's all for today. Thank you very much.